In match problem 2, we want to use the definition of continuity, so that formal definition that we established, to discuss the continuity of each of these functions at a specific point. So in part A, our given function is x plus 1, and we want to answer the question, is this function continuous at x equals 1? So we can start off by taking the limit of our function as x approaches 1. In this case, we have a polynomial function, so we can use direct substitution. To determine that that limit is 2. Similarly, we can evaluate the function at 1 and see that that function value at x equals 1 is 2. So since those two limits are equal to each other, since the limit as x approaches 1 and the function value at 1 are equal to each other, we can say that this function is continuous at x equals 1. So again, we have all three components of that definition met. The limit as x approaches 1 exists, the function is defined at 1, and the function value, the limit value are exactly equal to each other. We need all three of those things to be true. Now in part B, we want to consider the limit of a rational function, x squared minus 1 over x minus 1, at x equals 1. So if any of those three conditions that we used in part A fail to be met, we know our function is discontinuous. So in this case, we could start by considering our function value at 1. In this case, that would give us 1 squared minus 1 over 1 minus 1, which is going to end up being 0 over 0, that indeterminate form. So in this case, g of 1 is undefined. So it's, so it is discontinuous at x equals 1. So if the function value doesn't exist, the function can't be continuous. In part C, now we want to consider the continuity of our function at two different points, at x equals 2 and x equals 0. So we can start by considering our function value at 2. In this case, is going to give us 2 minus 2 over the absolute value of 2 minus 2, which again brings us back to that indeterminate form. So our function is discontinuous at x equals 2. So now we want to consider what's happening at x equals 0. We can start off by looking at our function value. H of 0 is going to give us 0 minus 2 over the absolute value of 0 minus 2, which will give us negative 2 over the absolute value of negative 2, or negative 2 over 2, which is negative 1. We can also consider the limit as x approaches 0 of x minus 2 over the absolute value of x minus 2. So here we have a rational function. We could again try direct substitution, which is going to give us 0 minus 2 over the absolute value of 0 minus 2, which is, again, going to give us negative 1. So since the function is defined, the limit exists, and those two values are equal to each other, this function is continuous at x equals 0.